Okay. All right, so going back to the PowerPoint and the question in the PowerPoint. So the question says, a sample of chlorine gas is found to be diamagnetic. Can this gaseous sample be composed of individual chlorine atoms? Well, basically, if you think about the chlorine atom and the electronic configuration of chlorine, it is 1s2, 2s2. By the way, the atomic number of chlorine is 17, right? So we have 17 electrons to play with. 1s2, 2s2, 2p6, 3s2, and then 3p5, right? Now, among the p subshells or subshell, you have 3p orbitals, right? I'm going to use the boxes to represent the individual p orbitals. And the way the electrons, the way the 5 electrons will be distributed among these p orbitals is like this: 1, 2, 3, 4, and 5, right? So we have a single electron here. So this is our unpaired electron. All right. So therefore, if the chlorine is composed of chlorine atoms, then you'd expect this to be diamagnetic, or I should say paramagnetic. My bad. Paramagnetic. All right. That's what you'd expect. But it says here that the sample is actually diamagnetic. So what does that tell us? It tells us that chlorine in nature is not made up of chlorine atoms. All right. Because if it was made up of chlorine atoms, it would be paramagnetic, because each chlorine atom will have one unpaired electron here. All right. So therefore, the conclusion is that the chlorine is not composed of individual chlorine atoms. In fact, as we all know, chlorine exists as Cl2, all right, a diatomic molecule. Okay, so that's a very simple question based on that particular topic. Okay, any questions about this? Any questions? Any questions? All right, so the next thing we're going to talk about, and I think this is basically going to take up the rest of this chapter, is periodic tables. And again, some of this you would have met before in introductory chemistry, but there are some additional things that we need to discuss, right? So when it comes to the elements in the periodic table, of course, we know that as you go from left to right and going down groups, what you'll find is that there are certain properties that will reoccur at regular intervals. In fact, that's a basis for the original periodic table that was first created by a Russian scientist by the name of Mendeleev, right? He noted back then, I don't remember exactly what year, certainly not the modern ages. Back then, they didn't know anything about the atomic structure. So the only thing that they have to go by in terms of identifying the different elements quantitatively in terms of their numbers would be the atomic mass. And Mendeleev was the first person who recognized that if you arrange the elements according to their atomic masses, after so many elements, you see certain properties repeating themselves, right? Now we know better, because now we know that, you know, based on the structures, we have the atomic number and so on, and therefore we can come up with a better version of the periodic table, which has undergone changes with the discovery of new elements and so on. So now we have our current version of the periodic table. But the same idea applies in that after so many elements, this time when they're arranged in terms of the atomic numbers, after so many elements, you're going to see certain properties repeating themselves, all right? And when we're talking about properties, we're talking about, you know, things like melting points and boiling points and hardness and even chemical reactivity in terms of different groups. So for example, elements in group 1, they tend to behave chemically the same way. They tend to react with oxygens to form oxides, and they tend to react with water to form basic solutions and so on. And we can see similar patterns in other groups, all right? So what we're going to look at is basically how we can observe and understand these different properties in relation to the electron configurations of the atoms in the periodic table, because after all, it is the electron configurations that allow us to come up with the periodic table, the current version of the periodic table. Okay, so a couple of properties we'll be looking at, the first of which is the atomic size. And this begs the question, how do we measure the size of an atom? So there are a couple of ways of doing it. There's one that is called the covalent radius, which is half the distance between the nuclei of two identical atoms joined in a molecule. So in this particular case, and I'm not sure which atom it is, I think this is the hydrogen atom or the hydrogen molecule. So to find the atomic radius, you take the distance between the two nuclei and divide it by 2, and that will give you the atomic radius in this particular molecule. Now, the metallic radius, if you're dealing with metallic elements, it's half the distance between the nuclei of adjacent atoms in the solid metal. So it's kind of similar to the covalent radius, but it applies to the structure in the case of a metal. All right. So what we're going to look at is how the atomic radius varies as you go from top to bottom down a group and left to right up a period. So let's deal with the group trends first, as far as atomic radius is concerned. And as you can see here, it says the atomic radius increases from top to bottom within a group, right? That is pretty much true without any exceptions, right? And that is related to the value of n. Now, n, of course, would be the principal quantum number. And more specifically, we're talking about the principal quantum number of the outermost shell, right? So as the value of n increases, moving down the periodic table, the distance between the electron in the valence shell and the nucleus increases. And that's what we look at in terms of making a prediction as to how the atomic size increases, all right? So that is true. I think I have some data here to, oh, that's later on. Okay, so that's basically it as far as down the group, how the atomic size changes. As you go down the group, the atomic size increases. Then we look at going from left to right of the periodic table. And what you'll find is that is as you go from left to right of any period, right? Period 1, 2, all the way down to 7, what you'll find is that the atomic radius decreases as you go from left to right, right? Now, how do we explain that? Well, if you think about it, as you go from one element to the next across a period, you're adding a proton to the nucleus. So for example, if you take period 2, it starts with lithium and ends with neon. Lithium has 3 protons. Then the next element, which is beryllium, has 4. Then boron has 5, and so on and so forth, until you get to neon, which has 10 protons in the nucleus. So you're adding an electron as you go from one element to the next within that period. At the same time, you're adding an electron to the same shell, right? So what's going to happen is that you're increasing the nuclear charge by adding a proton each time as you go from one element to the next. And those protons will have an increasing, or the nucleus, as a result, will have an increasing attraction for the surrounding electrons, right? So it's going to pull the electrons closer to the nucleus, including the electrons in the outermost shell. So that's basically the reason why, as you go from one element to the next, the size of the atom decreases. Now, the point being made here in this slide, it talks about the effective nuclear charge, right? Because if you look at and focus on the valence electron, and in this case, they're looking at sodium here and magnesium here. In the case of sodium, you're going to have 10 electrons in the inside, and then you're going to have 1 valence electron here on the outside here, right? So 1 valence electron, 10 inner core electrons, right? And what happens is that these electrons inside here will have a repulsive effect on the outermost electron. So basically, you have 2 forces in operation here. You have the attractive force of the nuclei of the nucleus for the valence electrons, and you have the repulsive force between the inner core electrons and the valence electrons. So basically, the effect that these inner core electrons will have is that they will be shielding the valence electrons. So the shielding effect will be the same for sodium and in the case of magnesium, because they have the same number of valence, or I should say the same number of inner core electrons. But the difference is that now the nucleus has 1 more proton, so the nuclear charge is greater here compared to here. So even though you have the same shielding effect here, the nuclear charge is greater here, will have a greater pull on the outermost electrons, and therefore the magnesium atom will be of a lower radius or lower size or smaller size compared to the sodium atom. And that trend continues in that period. In that case, it's period 3. So basically, aluminum will have a smaller radius compared to magnesium. Silicon will be smaller than aluminum, and so on and so forth. So the size decreases as you go from sodium to argon, with argon being the smallest in terms of size, all right? So that's basically the trend as far as atomic size is concerned. So just to recap, going down the group, the atomic size will increase. Going from left to right of any period, the atomic size will decrease. Okay, and this is just basically a graph which shows you basically the general trend that I just described. So in period 2, which starts with lithium and ends with fluorine. Oh, by the way, let me explain what this is all about. So the y-axis here represents the atomic radius expressed in picometers. And just to let you know or remind you what a picometer is, 1 picometer is equal to 10 to the minus 12 meters, all right? So just to give you an idea as to what we're talking about here. So as you can see here, the y-axis represents the, oops, come on. The y-axis represents the atomic radius, and the x-axis here represents the atomic number. And as you can see here, in the case of lithium, in period 2, and then continuing to fluorine in the same period, you see the atomic size decreases. The same is true for period 3. The same is generally true for period 4. There's a slight increase here, but it's generally there's a decrease. We won't go into the reasons why that is. And then you see something similar here in the case of period 5 and 6 with some, outliers, so to speak, in terms of atomic size, all right? So that's basically what is observed for each period, that the atomic size basically decreases as you go from left to right of any period. Okay, so based on what we have covered so far, we should be able to look at this example. It says with reference only to the periodic table. So we're just looking at the periodic table to answer this question. Arrange each set of elements in order of increasing atomic radius. So increasing, of course, means you're starting from the smallest size to the largest size, right? From the smallest to the largest. Okay, so we're using the periodic table. Let's look at A. They gave you magnesium, sulfur, and silicon. So which of these, based on their relative positions in the periodic table, would have the smallest size? Remember now, going from left to right, the size decreases of any period, in any period, right? So which one of these 3 would have the smallest size? Now, looking at the periodic table, magnesium, sulfur, and silicon are in the same period, right? So which one would be the smallest of these 3? You sure? Remember, the size decreases, goes, right. So sulfur will be the smallest, followed by what? Silicon, followed by magnesium. All right? So that's the answer for A. All right? What about B? B gives you arsenic. Where's arsenic? Okay, arsenic, nitrogen, and phosphorus. Now, in that case, they're all in the same group. And what did we say about the trend in atomic size in reference to groups? As you go down the group, what happens? The size increases, right? Now remember, the question is asking for the smallest to the largest increase, right? So which one will be the smallest between the arsenic, the nitrogen, and the phosphorus? Nitrogen, followed by phosphorus, followed by arsenic, obviously. And that's it, all right? Okay, and then the last one, C. Now in this case, they're not all in the same group and they're not all in the same period, right? You're given arsenic, antimony, and selenium, right? So let me see where, okay, arsenic is there, selenium is next to it to the right, and antimony is below it. So which of these would be the smallest? Remember, you're starting from the smallest to the largest. Selenium, followed by? Yes. And then antimony. Very good. And that's how you do that. All right. Any questions about those trends? Any questions? Any questions? All right, so let's talk about the ionic radii as compared to the atomic radius as a measure of the size of ions, right? So in this section, what we'll be looking at is correlating the size of ions to the atoms from which they are formed. But first, we have to define what we mean by ionic radius. So the definition is given right here. The ionic radius of each ion is the portion of the distance between the nuclei occupied by that ion. So for example, if you have magnesium outside here, this is the internuclear distance. And it turns out that in the case of this particular situation, the magnesium ion has a size or radius of 65 picometers, and that of the oxide ion is 140 picometers, right? So those are the radii for magnesium and the oxide ion. And the internuclear distance would be the sum of these two, which turns out to be 205 picometers, all right? So people have actually gone through the trouble of measuring the size of different ions, and we can therefore correlate the size of ions compared to the size of the atoms from which they're formed. So what we're going to look at now is observing and explaining why is it that there's a difference between the size of the ions and the atoms from which they're formed. And firstly, we're going to start off with looking at cations. Remember now, cations are formed as a result of an atom losing electrons, right? So what you'll find is that if you compare the size of cations to that of the atoms from which they're formed, you'll find that cations are smaller, right? And some examples are shown here. So this is a sodium ion, or I should say, sorry, the sodium atom. Its size is 186 picometers, but look here, the sodium ion is 99 picometers, almost half the size of the sodium atom from which it is formed. Let's look at magnesium. Magnesium has a size of 160 picometers, but over here, the size of the magnesium ion is 65 picometers. So this is even more than half the size of the original size of the atom, all right? Why is that so? Well, that explanation is actually given right here. When you remove electrons from an atom to form an ion, basically you have less electrons left. Less electrons left, meaning that there are less repulsive forces between the electrons, and therefore the electrons would be closer to the nucleus, and therefore the ion that is formed, or the cation that is formed, will be of a smaller size compared to the atom from which they're formed, all right? So that's the reason why magnesium ions are smaller compared to the magnesium atom, and the sodium ion is small compared to the size of the sodium atom, all right? So basically it comes down to less electron repulsion when you compare the cation to the anion, to the atom from which it is formed, all right? So that's as far as the cations are concerned. And if you understand this, then you will understand the trend when it comes to the anions, because it turns out that the anions are larger compared to the atoms from which they are formed. And the opposite reasoning will be applied. In other words, remember now, an anion is a negative ion which gains electrons, which is as a result of atoms gaining electrons. So if you're adding electrons to more electrons, more net repulsion will take place, and therefore the size of the anion will be larger compared to the atoms from which they're formed, all right? Okay, so for example, in the case of the chlorine atom, the size of the chlorine atom is 99 picometers. When it becomes a chloride ion, it becomes 181 picometers. So the ion is almost twice the size of the atom from which it is formed, all right? So that's what happens in the case of anions. Now, at this juncture, I want to introduce to you this term. It's called the isoelectronic species, or isoelectronic, that term. And basically, these are structures that have the same number of electrons, right? So basically, if you have one ion here and another ion here, and they have the same number of electrons, they're said to be isoelectronic. They don't have to have necessarily the same number of protons. As long as they have the same number of electrons, then basically they are said to be isoelectronic. And what you're going to see here is that when you compare ions and atoms that are isoelectronic, you're going to see that the size is dependent on the size of the nuclear charge, right? And basically what you'll find is that for two isoelectronic species, the one with the greater nuclear charge is the one that will be smaller, right? And again, if you think about it, it makes sense. If the nuclear charge is greater and the number of electrons are the same for two different species, the one with the greater nuclear charge will have a greater pull on the surrounding electrons, and therefore that species with the greater nuclear charge will be smaller. Now, the reason why I'm showing you this particular chart is that this gives you basically a very good representation of different elements, different atoms, and different ions and their sizes, right? And what we just discussed is basically summarized in trends that you'll observe in this particular chart. So let me just explain what's going on here. The purple spheres represents the atoms, right? The orange spheres here represents cations, and the blue spheres represents the anions, right? And these numbers here are basically the sizes expressed in picometers, the radii expressed in picometers, right? So remember the first thing I said was that going down any group, the atomic size increases. And we can see that here. If you look at lithium, its size is 152, and then sodium is 186, and then you have 227 for potassium, and it goes down and increases until you get to cesium, which is 265. And you see that in every group, right? The atomic size increases as you go down any group. And then when it comes to going across any period, the atomic size decreases. We talked about that earlier. We explained that. It decreases. And you can see that, for example, in period 2, starting with lithium, 152, and then beryllium is 111. Then we have 80 for boron, 77 for carbon, 75 for nitrogen, and so on until you get to fluorine, which is 71. So right across any period, the atomic size decreases, all right? Now, in terms of the relationship between ions and the atoms from which they are formed, we can see that in this table as well. So for example, let's focus on cations. In the case of cations, if you compare lithium to, if you compare the lithium ion to the lithium atom, you see that the lithium ion is 59, the lithium atom is 152, right? So basically you see that the ion is smaller compared to the atom if you're dealing with cations. And the same is true for sodium, potassium, beryllium, strontium, all the cations, indium, gallium, all these, when you compare the cations to the atoms from which they're formed, these cations are smaller. And then on the other side, when it comes to anions, as we said before, the size of anions, negatively charged ions, would be greater compared to the atoms from which they're formed. So you're going to see, for example, the nitride, which is greater in size compared to the nitrogen atom. Just to choose another arbitrary example, the selenide ion, 198, compared to selenium, which is 116, and so on and so forth. So basically, that is demonstrated here as well, the fact that negatively charged ions have a greater size compared to the atoms from which they are formed, all right? Okay, enough of that. So here's another example. Now, in this case, you're given these ions, all right? And the question is asking for you to do, again, using the periodic table and not the diagram I just showed you, just using the periodic table that we have access to, you're to arrange these in order of increasing radius, increasing. So again, we're starting from the smallest to the largest. Now, here's the key thing I would suggest when it comes to doing questions like these, where you're trying to find out the trend. What I would try to find out first are those that are isoelectronic, right? In other words, those ions that have the same number of electrons. So for example, the atomic number of calcium is 20, but it has a +2 charge, which means that there are 18 electrons here, right? In the case of iron, its atomic number is what? 26. So -3 electrons, so that would be 23 electrons here. In the case of potassium, its atomic number is 19, but it has a plus charge here, so this has 18 electrons, right? The sulfide here, sulfur has an atomic number of 16, but it has a -2 charge, so that has 18 electrons here. And then selenide, selenium has an atomic number of what? 34. So this has 36 electrons, right? Now, what I would do is focus on these, which has the same number of electrons, right? And then what I would do now is look at the number of protons each of them have. This has 20 protons, this has 19 protons, and this has 16 protons, right? So they're all well, not all. The 3 of them that I just circled are isoelectronic, but they have different number of protons, right? So let's deal with arranging them first, right? Which one of these would you expect to have the smallest radius? They have the same number of electrons. Which of these three? This one, and this one. Which of those three you'd expect to have the smallest radius? They have the same number of electrons, but the number of protons are obviously different. So which of these, calcium, potassium, or sulfide, would you expect to have the smallest radius? The calcium. Why? Because well, that's true too, but the main reason why is because it has a greater number of protons compared to the others. So therefore, because it has a greater number of protons for the same number of surrounding electrons, those protons will pull those electrons closer to the nucleus, right? So therefore, calcium, I would put here as having the smallest radius, and then I would follow that up with what? What would be the next element in line? Potassium. And then the next element would be sulfide, or the next ion, I should say. All right, so at least we took care of those three, all right? Now, the next question is, which would be, where would these two, let me put these in boxes. Where would these two lie in this series? Now, iron is where? Iron is in period 4 to the right of calcium. So I would put Fe3 plus here because it has a greater number of protons here. And then the selenide, it is in, hold on, wait a minute. No, wait a minute. I'll put the selenide above having a greater size than sulfide. And that would be the order. All right. So selenide would be above sulfide because selenide is below sulfur. Remember that trend increases going down the group. So the selenide would be the largest of these here. And then you have the others following. All right. Okay. Any questions about this? Any questions? Any questions? Okay. So the other trend we're going to look at is what is known as ionization energy. Ionization energy. What is that really? It is, as you can see on the screen here, it is the energy that is required to remove an electron from a ground state gaseous atom. In other words, we're talking about the energy that is required for this process here. So this is your atom in the gaseous state, and this is the reaction where an electron is being removed, and it forms a gaseous ion. The energy for that is called the ionization energy. The energy change for that is called the ionization energy, right? And ionization energy is usually expressed in kilojoules per mole of atoms. And you can have more than one ionization energy because, of course, you can have atoms with more than one electron. So a certain amount of electron is required to remove the first, a certain amount of energy is required to move the first electron, and then another amount of energy is required to move the second electron, and so on and so forth. And what you'll find, without exception, is that each time you remove an electron, more energy is required, right? So the first ionization energy to remove the first electron will be of a certain value, and then to remove the second energy, more energy is required. To remove the third electron, more energy is required, and so on and so forth, right? So basically, it's become more difficult to remove an electron each time. Now, what you'll find in certain trends is that there's usually a large jump in the ionization energy after the valence electrons are completely removed. And if you think about it, it makes sense because remember, the valence electrons are the electrons on the ones that are furthest away from the nucleus, right? So those electrons will not be held as closely to the nucleus as the other electrons. So therefore, when you remove those first electrons from the valence shell, then when you get to the core electrons, it becomes more difficult several times over to remove those electrons, right? Now, in terms of the first ionization energy, what you'll find is that as you go down any group, the first ionization energy decreases, right? And if you think about that, that makes sense as well. Because as you go down any group, the distance between the nucleus and the valence electrons increases, and therefore it is easier to remove those valence electrons, right? Because the valence electrons are not held as closely to the nucleus as you go down the group, all right? So as you go down any group, the distance between the valence electrons and the nucleus would increase, and therefore the attractive force between the nucleus and that electron would decrease, and therefore it becomes easier to remove those electrons. On the other hand, going from left to right of any period, the first ionization energy will increase. And that's because as you go from left to right of any period, the electron that is in the valence shell will be drawn closer to the nucleus, and therefore it becomes progressively more difficult to remove the valence electrons. Now, as far as that is concerned, there are some exceptions. And there are actually two exceptions that we're going to look at in regards to that trend. And our focus would be on period 2 for the purposes of examining those exceptions, right? But before we get to that, let me just give you some data here covering what we just talked about. So basically, what this is giving you are the first and second ionization energies of the elements in groups 1A and 2A. And what you're going to find is that, for example, let's compare lithium to beryllium, right? To remove the first electron, the amount of energy required is 520 kilojoules, right? But to remove the second electron, this is the amount of energy, right? And as you can see, it's several times over. In fact, let me calculate this here. 7298 divided by 520. Let me see what I get. That's 14 times over, right? So the amount of energy required to remove the second electron in lithium is 14 times that of the electron, the energy required to remove the first electron, right? Why is that so? Well, think about it. In the electronic structure of lithium, you have one electron in the valence shell. That's the electron in the outermost shell, right? So it is relatively easy to remove that electron. To remove the second electron, you have to go into the shell that is closer to the nucleus. And therefore, that's the reason why much more energy is required to remove that second electron. Now, if you compare that to beryllium, right? In the case of beryllium, to remove the first electron, that requires 900 kilojoules. To remove the second electron, that requires 1757. That's less than 2 times. In fact, let me see here, 1757 divided by 900. That's approximately 2 times, 1.95, right? So in that particular case, that difference between the first and second ionization energy in the case of beryllium is not as great as the difference between the first and second ionization energy in the case of lithium. Why? Because in the case of beryllium, the 2 valence electrons to be lost are from the outermost shell, right? So basically, you're removing 2 electrons from the same shell, so the energy difference required for removing those 2 electrons would not be as great compared to the case of lithium, where you need to remove 1 electron from the outermost shell and then the second electron from a shell that is closer to the nucleus, all right? And you see the same trend for comparing sodium to magnesium, potassium to calcium, rubidium to strontium, and cesium to barium, all right? In fact, in the case of, let me leave that alone. So that's basically how we can explain those differences between the first and second ionization energies for group 1A and group 2A elements, all right? Okay, and then this is showing you the trends in terms of going from left to right of periods. Now, in this row here, we're talking about period 2, and then this is period 3, right? So in the case of period 2, if you look at the first ionization energy, lithium is 520, and then it increases to 900 in the case of beryllium, and then it increases to 801 in the case of boron, and then 1086 in the case of carbon, and so on and so forth. Now, let me just say here that there are certain exceptions to the trend that I just mentioned. which I kind of glossed over, going from 900 to 801. So going back here, the first ionization energy increases from 520 to 900 in the case of beryllium, but it decreases from beryllium 900 to boron 801. So this begs the question, why is it that there's a decrease which contradicts the overall trend of increasing as you go from left to right in the case of beryllium going to boron, all right? And in order for us to answer that question, we have to look at the electron configuration of beryllium and compare it to boron. And let me squeeze that up here. So in the case of beryllium, the electron configuration is 1s2, 2s2. In the case of boron, the electron configuration is 1s2, 2s2, 2p1, all right? So if you compare these two, what you'll see is that in the case of beryllium, the electron to be lost would be lost from here, which is in the 2s subshell. But the electron to be lost in the case of boron will be lost from a p subshell. The p subshell is slightly further out compared to the s subshell. So as a result, it is easier to remove a 2p electron in the case of boron comparing to removing a 2s electron in the case of beryllium. So that's the reason why we have the first ionization dropping here from beryllium to boron, all right? Because the electron that you're removing in the case of boron is slightly further out from the nucleus compared to this electron here in the case of the 2s subshell in beryllium. And therefore, it is easier to remove that 2p electron compared to the 2s electron, all right? Now, there's another trend which is contrary to the general increase, and that is going from nitrogen to oxygen, all right? If you notice here, nitrogen has a first ionization energy of 1402, while oxygen is slightly less, which is 1314. Now, how can we explain that difference? Again, we have to go to the electron configuration for both nitrogen and oxygen. In the case of nitrogen, the electron configuration is 1s2, 2s2, 2p3, right? In the case of oxygen, it's 1s2, 2s2, 2p4. Okay, so obviously there's a difference between the electron configuration, especially with respect to the 2p sublevel. Now, how does that explain this decrease? What I'm going to do here to explain that is draw boxes to represent the p orbitals, right? So in the case of nitrogen, this is how the electrons will be distributed among the 2p orbitals. In the case of oxygen, this is how the electrons are distributed among the 2p orbitals. All right? Now, how does this explain this? Well, you have two electrons occupying one p orbital, so there's going to be some repulsion between them. As a result of that repulsion, it is easier to remove one of those two electrons here. So let me just make a note here. Repulsion will make it easier to remove one of these electrons. And because of that, the first ionization energy of oxygen will be slightly lower than expected and slightly lower than nitrogen, right? So that explains the decrease in the first ionization energy going from nitrogen to oxygen. And that explains also what happens here. The only difference is that the subshells will be different. This would be going from 3p3 to 3p4 in the case of sulfur. But it's the same idea where paired electrons occupying the same orbital will be repelling each other, and therefore it's easier to remove one of them to get the corresponding ion, and therefore less energy will be required, all right? Okay, so that's basically the trend as far as ionization energies are concerned. Any questions about this? Any questions? Any questions? Okay, let me just, so this is just basically a summary, graphically speaking, of the trends in first ionization energy. What we were looking at a while ago was going from lithium to neon, this is going from boron, from beryllium to boron here, where is a slight decrease. And by the way, this is the first ionization energy axis. This is the atomic number axis. So when you get to beryllium here, there's a slight drop from beryllium to boron, and then it increases, and then there's a slight drop from nitrogen to oxygen down here, and then it increases to neon. And you see a similar trend for period 3, and then it becomes a bit more confusing for the rest of the periodic table. So we won't pay attention to that part at this level anyway. All right, so some more questions here. Again, with only reference to the periodic table, we're going to answer these questions. So this question says, arrange each set of elements in expected order of increasing first ionization energy. So basically, again, you're going to start from the lowest to the highest. Which will have the lowest, and then you continue until you get to the highest. So let's start with A, magnesium, sulfur, and silicon. So based on their relative positions in the periodic table, which would you expect to have the lowest? Now, looking at this, magnesium, sulfur, and phosphorus are in the same period. So which would you expect to have the lowest ionization energy? Magnesium, followed by silicon, and then sulfur. Very good. What about B, arsenic, nitrogen, and phosphorus? Which would you expect to have the lowest first ionization energy? Arsenic, phosphorus, and then nitrogen. Very good. Okay, the next one, arsenic, germanium, and phosphorus. Where's germanium? Arsenic. Okay, arsenic, germanium, and phosphorus. Okay, so which would you expect of those three? Which would you expect to have the lowest first ionization energy? Germanium and arsenic are in the same group, and I'm sorry, germanium and arsenic are in the same period, while phosphorus and arsenic are in the same group. All right? So which of these would you expect to have the lowest first ionization energy? Okay, germanium, followed by arsenic, and then, of course, phosphorus. All right? So that's basically how that is done. All right? Okay, very good. Okay, another quantity that we're going to look at in terms of trends in the periodic table, electron affinity. We won't spend too much time explaining this. I'm just going to give you a general trend, and that's it. So let me define what electron affinity is first. Electron affinity is kind of like the opposite of ionization energy. It is the energy change when an electron is added to a gaseous atom. So we're talking about starting with the element, it gains an electron, and then you end up with the gaseous anion resulting. So the energy change occurring there is called the activation, I'm sorry, not activation, electron affinity. All right? And these values are negative because this process is always exothermic, right? And what you'll find is that nonmetals tend to have a greater affinity for electrons than metals, right? And that's because nonmetals like to form anions. So their electron affinity tends to be large and negative as a result, all right? So what you'll find in terms of electron affinity going across a period is that it tends to be more negative, right, as you go from left to right of any period, and as you go from bottom to top of any group. All right? So that's a general trend as far as electron affinity is concerned. So this is just a short table which gives you the trend that I've just described. So if you look at, for example, period 2, starting with lithium, you see that as you go from left to right, with certain exceptions, you'll find that the electron affinity becomes more negative. And as you go from bottom to top of any group, the electron affinity becomes more negative as well. I won't go into the reasons for that. That's just a general trend that is observed with certain exceptions, but that's generally what you'd observe, right? And that's all I'm going to say about that. Okay. So let's talk about some general discussions concerning metals. Metals, they tend to have a small number of valence electrons, usually no more than 3. So 3, 2, 1 electrons would be in the valence shell. So for example, aluminum will form an ion by losing those 3 electrons to form the aluminum ion, Al3+. All S block elements, meaning elements in groups 1 and 2, with the exception of hydrogen and helium, and all DNF block elements and some P block elements are metals, all right? So let's talk about metallic character, which is another thing that we can observe with respect to trends. The metallic character is actually related directly to the ionization energy, which itself is directly related to atomic radius. And what you'll find is that metallic character increases as you go down any group and as you go from left to right of any, as you go from right to left of any period, right? So this basically summarizes that particular trend with respect to metallic character, all right? Basically, the lower the ionization energy, the greater the metallic character. In fact, let me write that down here. The lower ionization energy implies greater metallic character. So that is something you may want to make a note of. All right? The lower the ionization energy, the greater would be the metallic character. So basically, as you go down the group, the ionization energy decreases. That means that the metallic character increases. As you go from left to right of any period, the ionization energy increases, which means that the metallic character decreases. All right? Okay. Some comments here about nonmetals. They tend to have larger number of electrons in their valence shells, usually 6 or more, 6, 7, 8. And they tend to form negative ions. All nonmetallic elements are P block elements with the exception of hydrogen and helium. And in terms of nonmetallic character, trends in the periodic table, it is opposite to metallic character, right? So if you understand metallic character and trends, then you can basically look at the opposite to see the trends in terms of nonmetallic character. In other words, it decreases going from left to right of any period and it increases as you go from bottom to top of any group, all right? And then we have a third category of elements known as metalloids. And these are basically elements that have some characteristics in common with metals and other characteristics in common with nonmetals. Now, for most legitimate periodic tables, excepting the one that we have in the classroom here, there's usually a line of demarcation which basically separates metals from nonmetals. In this periodic table on the screen here, that's this line right here, this stepwise line right here. So all elements, well, most elements to the left of that line would be metals. Most elements to the right would be nonmetals. But you have a few elements which are located on either one side or the other of that line, which are known as metalloids. And there are 7 of them, right? So we're talking about silicon, germanium, arsenic, antimony, tellurium, and astatine. And these are the polonium, not astatine, I'm sorry. Polonium is the 7th one. So these are basically the 7 metalloids. They have some characteristics in common with metals and other characteristics in common with nonmetals, all right? So they are indeed a minority group among the elements in the periodic table. So this is basically a summary of all the trends that we have discussed so far, all right? There's one more trend that we need to talk about, but that will come later. But this is basically a summary that you need to know of. So you could be asked a question like the types that I gave you before, where you're given 3 elements and you're asked, for example, to arrange them in order of increasing metallic character or decreasing atomic radius. This is what you're going to use to help you to make such predictions or to answer such questions, all right? What time is it? Okay. All right, so in fact, here's an example right here. So this question says, indicate which is the more metallic element, right? Now remember, the trend is going down, more metallic in a group, right? Going from right to left, more metallic in a period, all right? So calcium and barium, which one is more metallic? based on their positions in the periodic table, that is. Barium. Okay, very good. Antimony and tin, which one is more metallic? Tin. Germanium and sulfur, not silicon, sulfur. Germanium and sulfur, which one would you expect to be? Where's germanium? Okay. Which one would you expect to be more metallic? Germanium, exactly. All right. Okay, any questions about that one? Any questions? All right. Noble gases. This is a special group of elements which are located in group 8. And what they all have in common is that they're very unreactive, very stable. All right. In fact, helium and neon, they're not known to react with anything whatsoever, as far as I know. I haven't checked lately, but as far as I know, nobody has successfully performed any reaction with helium or neon. So they're very inert. In the case of the others, argon, krypton, xenon, and radon, they have succeeded in making compounds from those elements, but you have to use some real special conditions because once those compounds are exposed to the atmosphere, they break apart because they're very unstable, right? So that's what they do have in common. And the reason why they are very stable is because of their electron configurations, right? Which are very basically stable, all right? So as stated here, a few compounds of noble gases have been made, with the exception, as I said before, of helium and neon, all right? And that's all we're gonna say about those elements, because apart from that, they're not very interesting to talk about. All right, flame colors. Now, this test can be used to identify certain ions in aqueous solution, the flame test, right? And we can actually do some of that in the lab if we have the time to do it. But basically, all you have to do is take a wire, which is inert, and the usual wire that is used is nichrome wire, which is an alloy of nickel and chromium. And that's because nickel and chromium, they don't oxidize easily in the atmosphere. And then you dip that wire in a solution that contains your ion, and then you put that wire in a flame. And depending on the nature of the ions in the solution, you're going to get flames of different colors, such as lithium, giving this kind of reddish, pinkish, or I think they call it lilac colored, sodium, a yellow color, and so on and so forth. So these are really quite good in terms of indicating the presence of certain ions in aqueous solution. And the way this works basically in terms of what happens at the microscopic level is that when you put the solution in a flame, the heat of the flame basically gives energy to electrons, and they jump from one shell to the other, and that's an unstable excited state, and then it falls back to the lower shells. When it falls back, energy is given off in the form of radiation, which is in the form of lights of specific colors, as you can see here, all right? Okay. And then certain properties of elements with respect to their oxidizing or reducing properties. Halogens tend to be very good oxidizing agents, and the strength of their oxidizing power is related to the position of the elements in the periodic table, right? So basically what you'll find is that elements above other elements in that group would tend to oxidize the element that is below it. I think the example here is the chlorine. Let me write down the equation here. Chlorine reacting with the iodide ion to form the chloride ion plus iodine, right? If you bubble chlorine gas into a solution which is colorless and contains the iodide ion, I minus, then the reaction will result in the formation of chlorine, which is this purple solution right here, all right? This is a redox reaction, right? Because the chlorine is undergoing oxidation, is undergoing reduction, and the iodide is undergoing oxidation. So basically the chlorine is a stronger oxidizing agent compared to chlorine, all right? Okay, so that's as far as that is concerned. Okay. And then they're talking about the reducing properties of metals, basically. So the elements in periods in groups 1A and 2A, they are known to be relatively strong reducing agents. And one example of that is their reaction with water And what you'll find is that the reducing properties of these elements increases as you go down the group. So what is being shown here in these pictures is potassium added to water. And this is something that is very dangerous, depending on the size of the potassium piece you're using. If you add a small piece of potassium to something containing water, this is what happens. You have a very explosive reaction. And what happens is this. Right? And if you'll notice here that the potassium here, metal, which has a zero oxidation state, ends up with a +1 charge, and therefore, basically, the potassium is undergoing oxidation. All right? So that's what happens in this case right here. In this case, this is calcium. Calcium is not as strong a oxidizing agent as potassium. So what you'll find is that potassium reacts with water, but not as vigorously. And then this here is magnesium, which is basically unreactive if you add it to water. But if you heat it, then the reaction will take place. So that just goes to show you the relative strength of the oxidative, or I should say the reductive powers of these elements. The fact that the metals are strong reducing agents is related to their first ionization energy values being very low, and that's why these elements will easily lose electrons to reduce other substances such as water. And then we have different categories of what we call oxides. I'm just going to go through this quickly. We have acidic, basic, and then we have amphoteric oxides. Acidic oxides are usually oxides of nonmetals. When added to water, they form acidic solutions. Basic oxides are usually oxides of nonmetallic elements, and they form basic solutions when added to water. And then we have a third category of oxides, which are known as amphoteric oxides, and that's because they can react with either an acid or base, depending on what they're reacting with to form products. All right, so that's basically the difference between these three types of oxides. As far as amphoteric oxides are concerned, they're usually formed as a result of certain metalloids and some of the heavier metals like lead, aluminum, gallium. They tend to form amphoteric oxides. Other metallic oxides tend to be basic, and of course, the acidic oxides tend to be formed as a result of, as I said before, non-metallic elements combining with oxygen. Okay, so that's basically it as far as this chapter is concerned. And that means that for this assignment, I don't have that copy of that assignment here. So you guys are still on assignment 8. So let me just check it out here to see if I missed anything. I don't think I missed anything in terms of topics covered. So assignment 8. Okay, so you should be able to do these right here. Okay, ionization energy. Okay, you should be able to do those. All right, so basically that's it as far as this assignment is concerned. All right. So nothing much else to talk about. So I'm just going to call it a day. So make sure you complete this assignment, and let me open up a Dropbox for this here. Oh, I did already. Oh no, I need to set the date. Okay, so today is the 2nd. I'll let it be due on Monday. Oh, shoot. What am I doing? Today is the 7th. Yeah, Monday, the 13th. How could I forget? Yesterday was my sister's birthday, so. All right. So that's it for today, folks. See you guys on Thursday.